Hi. Now in today's class we will go through effect of substituents on acidic strength of carboxylic acids, right? Now when we talk about acidic strength, from the very basic definition of acids, we know that acids are those substances that releases hydrogen ions in solution, right? More number of hydrogen ions you have in solution from a compound, the more acidic it is, right? So when we say more number of hydrogen ions, that means that compound can easily release hydrogen ions, right? So what substituents will do, some substituents will make release of these hydrogen ions easier in solution, whereas other substituents will make release of these hydrogen ions difficult in solution, right? Now how this release of hydrogen ions by substituents are made difficult or easier, we'll look into the reason, right? We'll look into that explanation. So for any acid, let's look at the structure to understand from where exactly this hydrogen ion is released, right? Let's take this acid, acetic acid, right? Right? When we say hydrogen ion is released, right, from carboxylic acid, it is released from this bond. This OH bond will break and this hydrogen ion will get released, right? And it will form this acetate ion, right? This is a resonance hybrid. We have studied this in previous lecture when we studied its structure. This acetate ion has a negative charge, right? And when this bond will break, hydrogen ions would be released, right? It is due to this hydrogen ion that this acid is your carboxylic acid is acidic in nature due to the presence of this hydrogen ion, right? Which is released due to the dissociation of this OH bond, right? Now we'll study that how substituent in this case is this methyl group, right? And if you want to write down this reaction for any generic carboxylic acid, we'll take the generic formula. Instead of methyl group, we'll write R, right? And instead of here in acetate ion, we write R, right? Now when we say acidic strength, this acid in solution will undergo ionization to give you this ion, carboxylate ion, that has a negative charge, and your hydrogen ion, right? Now substituent, this is your substituent. We'll see how this substituent will affect the acid strength, right? This is your substituent. Now there are two things. If you look at this reversible reaction, this is a reversible reaction where these two ions will recombine to give you back this unionized molecule, right? Now if this substituent can do two things. It will make the release of hydrogen ions easier or difficult by making this OH bond weaker or strong bond, or it will stabilize. The other thing is it will stabilize this ion, right? This carboxylate ion by dispersing its negative charge, right? Or by intensifying its negative charge, right? So the substituent, what the substituent will do, it will do two things. First thing is it will strengthen means it will make the bond strong. It will strengthen or weaken OH bond, right? Second thing is it will intensify negative charge on this carboxylate ion. When it will intensify negative charge, that means the ion will become unstable, right? Because when this is more negative, it is unstable. It will combine with hydrogen ions to give you back this unionized acid molecule. It will intensify or disperse negative charge on this carboxylate ion, right? So when it will intensify the negative charge, it will destabilize this carboxylate ion, right? And when it will disperse the negative charge, it will stabilize this carboxylate ion, right? Now let's study how this substituent, right, the types of substituents and how it will do these two things: intensify the negative charge or disperse the negative charge, or how it will strengthen or weaken the bond in order to make the release of hydrogen ions easier or difficult. Let's first talk about electron substituents. Are of two types, right? First is electron releasing substituents, right? The second is electron withdrawing substituents, right? Electron releasing substituent, let's take example of methyl group, right? And electron withdrawing substituents are halogen atoms, let's like fluorine, chlorine, bromine, iodine. All these are substituents, right? Now let's take one example of acetate ion, right? Acetic acid, CH3 C double bond OH, right? Let me just write it here. It's CH3, right? Like this. This is a resonance hybrid. So this is your acetate ion that has a negative charge, and this bond will break to give you hydrogen ions. Now let's see how this substituent, right, which is your electron releasing substituent, will affect it, right? This is an electron releasing substituent, so it will release electrons towards carbon and oxygen, right? Oxygen of this OH bond. So it will intensify the negative charge, right? Intensify the negative charge on this oxygen atom, right? Now just understand that when we talk about this bond, right, release of hydrogen ion or acidic nature is due to dissociation of this bond, right? Now this substituent will either strengthen this bond, right? If this substituent will make this bond a strong bond, then the dissociation of this bond will become difficult. That means release of hydrogen ions will become difficult, right? Now if this substituent will make this bond a weaker bond, then release of hydrogen ions will become easier. In this case, when we have an electron releasing substituent, right, the bond will become a strong bond, right? How it will become a strong bond? Just understand from basic chemical bonding that a bond, right, this bond is formed, OH bond is formed due to pair of electron. This is formed due to coordinate, this is a coordinate bonding, but after a coordinate bond is formed, it is indistinguishable from a covalent bond, right? So you have a bond pair of electron between oxygen and hydrogen. Now this bond is due to this bond pair, right? This bond pair. Now this bond pair equally attracts this hydrogen atom and this oxygen atom, right? And it is this bond pair of electrons due to which these two atoms, oxygen and hydrogen, are held together, right? Now if this bond pair of electron, ideally it is in the center, if this bond pair is somehow due to something is moved towards oxygen atom, right? Now since this is away from hydrogen, when it will move towards oxygen atom, it is away from hydrogen, right? So it has less control on hydrogen. It will attract hydrogen with a less force, right? Since this attract hydrogen with a less force, right, this hydrogen can be easily released if this bond pair will move towards oxygen atom, right? because it is away from hydrogen, less force of attraction. So less force of attraction means this hydrogen can be easily released, right? Now if this bond pair of electron remains here or it moves towards hydrogen atom somehow, right, then it has more control on hydrogen atom. It will attract hydrogen atom more strongly, right? So when it will attract hydrogen atom more strongly, this bond will become a strong bond. And this here, when this bond pair move towards oxygen atom, this bond will become a weak bond. And this hydrogen atom can be released easily. Right? Here, this hydrogen atom would not be released easily. Right? So, this kind of situation will make the acid a strong acid. It will make the acid a strong acid because this hydrogen atom can be more easily released. Since here this hydrogen atom, this bond is weaker bond, this bond has become strong bond because this bond pair is in the middle or towards hydrogen atom, right? Now when this bond pair is in the middle or the force of attraction between this bond pair and hydrogen is more, then the release of hydrogen atom from this bond will become difficult, right? When the release of hydrogen will become difficult, that means it will make it a weak acid, right? This is the basic thing. Now this is substituent. Let's come back to this. This is a substituent. What it is doing is it is releasing hydrogen atom, it is releasing electrons towards carbonyl carbon and oxygen. So this release of electrons, right, is due to, firstly this is due to plus I effect. We call it as inductive effect of methyl group. Due to plus I effect, it will release electrons towards carbonyl carbon and oxygen. When you have more negative charge, right, or electron density will increase on this oxygen atom of this OH bond, right? It will make this bond a stronger bond. How? Because you have a bond pair here and you have a negative charge here. So negative, and this bond pair is also an electron pair. This is negative, right? So there is repulsion. This bond pair, when there is repulsion between this bond pair and negative charge on the oxygen atom, this bond pair will not move towards this oxygen. It will remain in the center, or it will move towards hydrogen atom, right? So this bond is a strong bond, this situation, right? So when we have a strong bond, it's a weaker acid, right? So presence of this methyl group in acetic acid will make this a weaker acid, right? And we know that we say that acetic acid is a weak acid. Now we understand why it's a weak acid, right? Because earlier in our previous junior classes we used to say this is a weaker acid because these acetate ions and hydrogen ions combine back to give you acetic acid, right? We'll understand that also, how that happens. Now we understand one thing, that this is a weaker acid. Why? Because this methyl group will make this bond, OH bond, a stronger bond, due to which release of this hydrogen ion will become difficult, right? So electron releasing substituent due to plus I effect will increase electron density at oxygen atom and carbonyl carbon, right? Now the presence of negative charge onto this oxygen atom will strengthen this bond, and we have understood how, right? Thereby making the release of this hydrogen ion difficult, right? And the acid will become a weak acid, right? And the other thing that it will do is, now when this hydrogen ion is released, what it will form is, this is an acetate ion plus hydrogen ion. Now this is an electron releasing substituent, plus I effect, right? It will intensify negative charge onto this acetate ions, right? Intensify the negative charge. When the negative charge is intensifying, negative charge means since this is releasing electrons, so it will increase negative charge onto this carboxylate ion, right? Onto this acetate ion. We call it as acetate ion. When the negative charge is increased, you have a positive ion here. So this will immediately combine with this hydrogen ion to give you back this unionized molecule. So you have less hydrogen ions because acetate ions will combine with hydrogen ions to give you back acetic acid, right? And why it will immediately combine with hydrogen ion? Because it has more negative charge due to the presence of this electron releasing methyl group, right? So what we say is that this methyl group will intensify or increase negative charge, thereby making this acetate ion unstable. Since it is unstable, it will immediately combine with hydrogen ions to give you back acid, right? That is why your acetic acid is a weaker acid, right? So here this methyl group will intensify negative charge or increase the negative charge, right, and will make this acetate ion unstable, right? This is your unstable ion, so it will immediately react with hydrogen ions to give you the reverse reaction. I hope this is clear. So in general, we say that electron releasing substituents, right, will strengthen the bond, strengthen your OH bond, right, and will decrease the acid strength. Decrease acid strength, right? It will decrease the acid strength. It will decrease the acid strength, and two things it will do is it will destabilize. It will destabilize your carboxylate ion, right? And the other thing is it will strengthen this bond. Due to these two things, this acid is a weaker acid, right? Due to these two things, we have less hydrogen ions. Less hydrogen ions means acid is a weaker acid, right? I'll repeat quickly. When we say acid strength, right, when we say the acid is a weaker acid, like we say for acetic acid, that means we have less hydrogen ions. Why less hydrogen ions? Because ions are released by dissociation of this OH bond, right? Now the presence of this electron releasing methyl group will strengthen this bond, will make this bond a stronger bond, due to which release of hydrogen ions will become difficult, right? And we have less hydrogen ions, that means less acidic, right? That means the acid is less acidic. Now this carboxylate ion, coming to this, since it is an electron releasing substituent, so it will increase the negative charge onto this acetate ion. When we have more negative charge on this acetate ion, or the negative charge is intensified on this acetate ion, right, it will become unstable and will immediately combine with this hydrogen ion to give you back this acetic acid. That is why acetic acid is a weaker acid, due to the presence of this electron releasing substituent. Right, now let's come back to formic acid. We say that formic acid is a strong acid compared to your acetic acid. Why? Because formic acid has a substituent hydrogen ion. Now this hydrogen ion is not an electron releasing substituent, right? So when you look at its dissociation, you have this formate ion and you have this hydrogen ion, right? So since this is not electron releasing, right, it will not intensify negative charge on this formate ion, right? So this hydrogen ion will not make this formate ion unstable, right? So it will not immediately combine with this hydrogen ion to give you back formic acid. And the second thing is, since this is not electron releasing, so it will not strengthen this OH bond, right? So release of hydrogen ion or dissociation of OH bond is easier in case of formic acid compared to acetic acid, right? So we say that your formic acid is stronger than acetic acid, right? Now we know the reason why. Because formate ion is more stable, right, than acetate ion. And the second thing is, there is no electron releasing substituent attached to the carbonyl carbon, right, that can destabilize the formate ion, right, or that can strengthen this bond. There is no electron releasing substituent attached to this carboxyl carbon, right? This carbon atom that can strengthen this bond, like it happened in case of acetic acid. So formic acid is stronger than acetic acid. This is an important question. This has been asked in exams many times, why formic acid is stronger than acetic acid, right? This is the explanation. Now, the other important thing that we need to look at is, here this acid has only one methyl group, right? Now suppose it has more methyl groups, right? Suppose this is the acid, right? It has two methyl groups, right? So both methyl groups, let's write it like this. Right? So in this case, when you have two methyl groups, then both the methyl groups are your electron releasing, right? Since both these methyl groups, right, both these methyl groups are electron releasing, right, then it will intensify the negative charge more, right, compared to acetic acid, right? I hope this is clear. Right, let me just correct this. Sorry, this is like this, right? Since you have more electron releasing substituent, methyl group, this is the methyl group, right? Both will release electron towards this carbon and towards this oxygen, right? So more electrons would be released, it will intensify this negative charge on the ion more compared to acetic acid, right? And it will strengthen this OH bond more compared to acetic acid. Now suppose we have this acid, now we have three methyl groups, right? All these three methyl groups are electron releasing. So it will strengthen this OH bond to the maximum and will intensify the negative charge to the maximum, right? This will make, due to the presence of three methyl groups, this is the weakest acid, right? So if you compare this acetic acid right, if you compare this acetic acid with these three, acetic acid would be the strongest acid, right? Then this acid and this acid is stronger than this acid, right? I hope this sequence is clear. As the number of methyl groups will increase, their electron releasing tendency will increase. More electron release would be done towards oxygen and this carbon, right? That will strengthen this OH bond more, right? And more electron releasing groups means this ion will become more unstable, right? Or the negative charge would be intensified more, right? In case of three methyl groups. So that will make this most unstable, which will immediately combine with hydrogen ion to give you back the unionized acid molecule, this molecule, right? I hope this is clear. Now let's come back to electron withdrawing substituent. How will electron withdrawing substituent will affect? Electron withdrawing substituent, suppose I take fluorine, right? Like I said here, if we somehow move this bond pair towards this oxygen atom, it will make this bond a weaker bond, right? How? Because when it will move away from hydrogen atom, right, this bond pair will have less control on hydrogen atom, right? So less force of attraction means this hydrogen atom would be easily released. This is what this electron withdrawing substituent will do. This electron withdrawing substituent, we know that fluorine has high electronegativity, right? And electronegativity means ability to attract electron towards itself, right? So this fluorine will attract electron towards itself, right? So this bond pair will also move away from hydrogen atom. So this bond will become a weaker bond, right? So when this bond will become a weaker bond, the release of this hydrogen atom will become easier. And if we look at fluoroacetate ion, this, right? Looking at the second thing, what about the intensity of negative charge? The intensity of negative charge will also go down, right? Why? Because this negative charge would be dispersed when you have an electron withdrawing substituent, right? That is, it is less on these oxygen atoms, right, and carbon. Now it is shared by this fluorine atom also, negative charge. So we say that this negative charge is dispersed when you have an electron withdrawing substituent. So you have less negative charge on to this oxygen, right? So this ion will become stable and it will not immediately combine with hydrogen ion, right? Because negative charge in this case is dispersed onto the molecule, right? So this presence of this electron withdrawing substituent will make this a stable ion, right? It will make this a stable ion, right? And second thing is, it will make this weaker bond, right, by withdrawing the electrons towards itself. When the electrons would be withdrawn towards fluorine atom, this situation will become true, right? And when the bond pair will move more towards oxygen, the release of hydrogen ions will become easier. When release of hydrogen ions will become easier, that means now more hydrogen ions would be available in solution, so the acid would be a stronger acid. So presence of electron withdrawing substituent will make the acid a stronger acid. Electron withdrawing substituent will make the acid a strong acid, right? Now let's compare it with other halogens. We know fluorine is most electronegative compared to other halogens, right? So we have three things: the presence of for electron withdrawing groups, nature, position of electron withdrawing groups, right? So this electron withdrawing thing is known as minus I effect. So fluorine, due to minus I effect, will weaken OH bond and stabilize this fluoroacetate ion. Fluoroacetate ion, right? It will strengthen this fluoroacetate ion, due to which it will stabilize the fluoroacetate ion by dispersing the negative charge. Since this is electron withdrawing, so it will disperse the negative charge, right? That will make it a strong acid, right? Now there are three things: the nature, right, and the position of this fluoroacetate ion. The position of this halogen atom and the number of halogen atoms. It's simple. Nature, when we say nature, electronegativity, right? More electronegative this atom is, more strongly it will attract this electron density towards itself. More strongly it will attract the electron density, that means more stronger is the acid, right? So this is the sequence of electronegativity, right? So acid that has fluorine atom would be more stronger, because this has ability to attract the shared pair of electrons maximum, right? So this would be stronger acid compared to this, and this would be stronger than compared to bromoacetic acid, right? These questions are asked many times. This is very important. Now position. When we talk about position, if this acetate ion is far away from this, if this halogen atom is far away from this carbon atom, the more away this halogen atom would be from this carbon atom, less would be